Good morning, everyone. Today we are going to discuss about Introduction to Non-Traditional Machining. I am Pritam, Assistant Professor, Department of Mechanical Engineering, Haldia Institute of Technology. So, welcome to the course of NTM. So, what is NTM? NTM, that means non-traditional manufacturing or non-traditional machining. It is basically a quite new technology. Nowadays, advances in different types of material like hard material or different types of alloy which are very hard and uh, very chemically non-active material or chemically stable material. Those material cannot be machined by using conventional machining process like turning operation in lathe machine or milling machine, by using drilling operation by drill bit. So that's why we need some new technology which is non-traditional machining. In this non-traditional machining, the basic principle of the conventional or the traditional machining is that the hardness of the tool will be more than the hardness of the workpiece. But in these cases, most of the time, the tool does not touch the workpiece. So, as a result, the hardness of the tool and hardness of the workpiece does not depend on each other. Okay, so that is the main advantage of this non-traditional modern manufacturing. So, what is the classification of non-traditional machining? Depending upon the power source of the machining, we can classify into four division. In case of conventional machining or the traditional machining, the main power source for machining is the electric power, like for lathe machine or milling machine, where the relative motion between the tool and the workpiece remove the material from the workpiece. Now, over here, it can be classified into four categories. The main power source may be mechanical. In case of mechanical, where the high pressure of the abrasive material or the jet will strike on the work surface, and as a result, the material will remove from the workpiece. So the energy source is the mechanical energy. Now there may be a third energy source. In case of thermal energy source, the thermal energy will be applied on a particular area. In particular area, the temperature of that workpiece will be increased, and it will actually melt and vaporize the workpiece material by using the fusion process. So as a result, the removed material or the burnt material will be flushed away by some flushing pressure or by some flushing equipment. Then there is another type of a source for non-traditional machining is the electrochemical machining. It is basically the reverse electroplating operation, and we will discuss later in details. And there may be some chemical energy source. This is actually chemical attack or chemical etching process, where the particular area of the workpiece surface will be removed or will be polished, and other layer of the surface will be removed or other layer will be masked using some protection. Okay, these are the different four types of source of non-traditional machining. Okay, classification. So the classification, so depending upon the power source, what we have already discussed. So the for the mechanical energy source, we can use USM, that is ultrasonic machining, water jet machining, and abrasive water jet machining, which is a combine of the ultrasonic machining and water jet machining. Then there is IJM. It is not very convenient, but in most of the industry we use ultrasonic machining and water jet machining either individually or both in the same form, like abrasive water jet machining. It is quite a new and hybrid type of machining process. Now for the thermal energy source like EDM, EBM, EDM is the electric discharge machining, EBM is the electron beam machining, and plasma beam machining, laser beam machining, ion beam machining, those are the energy consumed from the thermal power source. Okay, so the basic principle of this type of machining is they will melt and vaporize the metal, and burned material will be removed by some flushing pressure. Now, in case of chemical and electrochemical, they are grouped in a same manner. They CHM, PCM, ECM, like that. They are chemical etching process basically. where the main difficulty of the chemical machining process is that the material removal rate is very slow. So mechanical machining, what we have already discussed, that mechanical machining is ultrasonic machining and water jet machining. In ultrasonic machining, where the small particle of abrasive material will strike on the work surface. Suppose this is a work surface, from a nozzle the small particle will strike on the work surface and it will create a cavity or groove, and it will remove the material from this surface, and the removed material will be flushed away by the pressure. And in case of water jet machining, the same principle occur, whereas instead of this abrasive particle, what we use is we use the high jet or a high water pressure. In thermal machining, what we have already discussed, it can be classified into basically 5 categories. First one is the EDM. EDM is the electric discharge machining. In electric discharge machining, it will happen in the dielectric medium, where the workpiece and the electrode both will be submerged in the dielectric medium. Whereas in case of EBM, that is electron beam machining, the workpiece and the electrode, that will be in a medium which is vacuum. Whereas in case of EDM, it is dielectric medium. In case of EBM, we use the vacuum. And in case of laser beam machining, the same thing will be happen in the air medium. Okay. In case of PBM, that is plasma beam machining, the plasma will generate in a particular gases, and we will discuss what will be the advantage and disadvantage of these different types of machining. Similarly, for IBM, ion beam machining, it can be in the vacuum. So EBM and this IBM, these two type of machining can be only in vacuum, whereas in case of LBM, we can do in the open air. So this is the main advantage of the LBM. And in case of EDM machine, we have to use the dielectric fluid like E30, that is a industry grade EDM oil, or you can use distilled water or heavy water as a dielectric medium, or you can use kerosene as a dielectric medium. Now, chemical and electrochemical machining. In chemical and electrochemical machining, this is basically the chemical milling or the photochemical machining process, or it will be a chemical etching process. In chemical etching process, what happens? The particular layer or the surface of the material will be removed. Basically, in case of ECM, electrochemical machining, it only happen in the dielectric fluid, electrolyte. Okay. The next one is water jet machining. So already we know what is water jet machining. The source of the energy is the hydraulic pressure. So the main source is the mechanical energy, the pressure energy. This pressure energy, so from some source or water source, this water goes through a nozzle or through a pipe channel which is controlled by a valve. Through this valve, we can control the pressure of the water, and that water will come through this nozzle in this direction. So when this water strike on this surface, what happened? Due to the high energy, the kinetic energy of the water will create a distortion on the workpiece surface, and as a result, some material from the work surface will be removed. It does not depend upon the thermal conductivity of the workpiece, does not depend upon the hardness of the workpiece. So, regardless of those matter, the material can be cut into two pieces, or we can create a small drill over a heavy duty or a very hard material. So, basically, the control parameter, the range of the parameter, like the nozzle diameter, it varies between 0.1 to 0.4 mm, which is very difficult to drill in conventional machining process. So this is the main advantage of the water jet machining. And the pressure is 400 megapascal. The velocity is 900 meter per second. This is the velocity of the jet, water jet. And we use a pump. So these are the basically these parameter govern the machining quality or the surface quality of the workpiece. Now, abrasive jet machining. Also, this is one type of mechanical energy source machining, where instead of using the water jet, we use some abrasive particle along with either water or high pressure fluid or normal gases. So, this is a gas supply. From this supply, the gas will flow through this pipe where there is a powder mixture chamber. In this powder mixture chamber, there is some abrasive particle. This abrasive particle is filled with this chamber and it is always in a vibration. So when the gases passes through this chamber, the powder will mix with the gases and it will flow through the nozzle, and from here it will strike over the surface, and as a result the striking force will remove the material and the removed material will be flash away in this manner. So basically the working principle of the abrasive jet machining and the water jet machining are quite similar. Okay. In this case, the abrasive particle we use as the tool, cutting tool. So what happens when the abrasive particle strike on the surface of the workpiece, it will create a cavity. But as we know, the high pressure will impact on the workpiece and it will actually create a crack over the surface, and that crack may propagate through the workpiece in this manner. So there is a high chance that it may create an internal stress or internal crack of the workpiece. So there is some disadvantage of this abrasive jet machining, but the main advantage of the abrasive jet machining is that it does not depend upon the hardness of the workpiece. So we can actually remove any material from any high difficult to machining ceramic or any hard alloy material. Okay. Then similarly, there is some process parameter, there is some control parameter, there is some response. So the main response is the MRR. So we have to always increase the MRR. We have to always look the geometry of the cut and what will be the surface finish and what will be the nozzle wear of machining. And how we can control this thing? We can control this thing by some control parameter. So these are the basic control parameter, like the abrasive particle, the gas, and nozzle quality. That means nozzle material, nozzle geometry, and what is the inclination or the impact angle. So depending upon this, we can actually govern the machining condition. Then ultrasonic machining. So ultrasonic machining is basically an ultrasonic vibration of between the tool and the workpiece. So here this is a workpiece and this is a tool. This is a cutting tool. So there is a random vibration between the tool and the workpiece. So when the tool vibrate in a high frequency with low amplitude, there is some bloody material or the abrasive material which come from the tool, and that will strike on the workpiece, and in this manner the workpiece will be removed. So this is basically, you can say, the source is the mechanical energy, the high impact or the ultrasonic vibration. So these three are almost similar. So mechanism. So first the hammering of the abrasive particle, then the free abrasive particle create a high impact on the workpiece surface and it create a cavity on the workpiece, and then chemical action associated with the fluid or the gas will remove the material. So basically the working principle are quite similar. Now we can calculate the material removal rate. This is denoted in the volumetric material removal rate. That means it is gram per minute or gram per second. So Q is the material removal rate, which is directly proportional to the capital V Z V. Capital V denotes the volume of the work material removed per impact, means the single impact volume removed, Z is the number of the particle making impact per cycle, and V is the frequency. As we know, the frequency is very high but the amplitude is low. So generally the frequency will be very high, but the number of particles making the impact per cycle, if we increase this number, then what happens? There is a slight chance that it will actually block the nozzle. So there is a limitation of this Z. So that's why we cannot increase the MRR as much as we want. So there is some limitation that we can increase the MRR, but it will be up to some limit. Now, electrochemical machining process. So this is very most common type of non-conventional machining process, which is nowadays used in the heavy industry also. It is used in the medical science also. Okay. Now, what is electrochemical machining? The energy source of the electrochemical machining is basically the chemical machining. So, from the name we can say that it is some chemical machining where it is just reverse electroplating. We all know the electroplating, so it is just the reverse electroplating and it is based on the principle of the electrolysis. So what happened? What is the machining process? So we will discuss over here. So basically we can see this is a schematic diagram of the ECM setup where this is a workpiece, anode, and this is a tool. This is a cutting tool. This one is a cutting tool. This cutting tool is connected with the negative power source. Cathode and the workpiece anode is connected with the positive power source. Both the workpiece and the tool, they are submerged in this electrolyte. This electrolyte solution, for a common example of electrolyte solution is NaCl solution. So this workpiece and the tool both are submerged in a electrolyte solution where this electrolyte will flow through this channel where we have a pump. This is a pressure gauge. There is some controller. So this fluid will flow through this channel. So when the tool and the workpiece are submerged in the electrolyte solution and when the tool is moving in the downward direction, what happens? So there will happen that the electron will actually flow in this direction and that electron flow will actually chemically etching operation, and as a result there will be exact replica of the workpiece. The exact replica of the tool will create on the workpiece. That is the main advantage of the chemical machining process. So in chemical machining process, it depends upon the two basic law. That basic law of the Faraday, that the amount of the chemical change produced by an electric current, that is the amount of any material dissolve or deposit, is proportional to the quantity of the electricity passed. Okay, this is the basic principle of the Faraday. And the second is that the amount of different substance dissolve or deposit by the same quantity of the electricity are proportional to their equivalent weight. This is depend upon the chemical equivalent weight. So these are the main governing equation for the ECM process. So by using this equation, we have calculated the MRR, that is material removal rate of ECM process. Similarly, in earlier case, we have calculated the MRR. Over here also that MRR is calculated and it is in the form of the material removal, that is volume of the material removal per unit time. So basically gram, you can say it is gram per second. Okay, or basically you can also convert into in millimeter cube per second or per minute. Okay, so both we can calculate. So over here the material removal rate during electrolysis process, M equals to ITE by F, where F is the constant, it is the Faraday constant, and M is the amount of the material removal in gram. So M is in gram, so this equation will be the gram per minute or gram per second. I is the current in ampere flowing through the spark. Then T is the time of the current through which the spark is on or the current is passing, and this is M is the Faraday constant, and E is the chemical equivalent, chemical gram equivalent. So using this equation we can conclude that M is the MRR for the ECM process. Now another non-conventional machining process is electric discharge machining. In electric discharge machining, it is quite similar to the ECM process, but there is minor difference between ECM and EDM. The main difference is it is a discharge machining. That means there is a spark between the tool and the electrode. The spark is actually create a temperature rise in the workpiece. Okay, so how does this process happen? We'll see that this is a schematic diagram of the EDM process, where this is a tank. In this tank, the workpiece and the tool, they are submerged in a dielectric fluid like kerosene, hard water, or EDM oil 30, which is conventionally used in industry. So this workpiece is connected to the power supply. Similarly, it is an anode and the tool is a cathode, that is negative, and this is a positive source, and this is connected to the negative source. This is positive source and this is negative source. So this tool is controlled by the servo controller. Basically, it is moving the tool in the upward and downward motion. And this dielectric fluid is not a stagnant fluid. This dielectric fluid is actually in a flowing manner. So when the current is passing through the tool and the workpiece, what happens? The free electron, as this is a metal, the free electron will actually start to move in this direction. And when huge number of electrons start to move in this direction, what will happen? It will create a plasma channel. This plasma channel will strike on the workpiece surface. In this surface, the temperature of the workpiece will increase, and it will increase so high that the metal will melt and vaporize, and within an instant. And then this removed material will be flushed away by the dielectric fluid. So this is the main principle of the EDM. Now similarly, we have calculated the MRR of EDM. Now this is typically a single spark condition we have considered, that where the tool is actually creating a single spark on the workpiece, and due to which there is a cavity, a small cavity. You can see this thickness or the radius you can assume as R. Okay. Now due to this single spark, this cavity will happen, and you can see we can calculate the volume of this cavity. It is 2/3 of pi r cubed, where r is the radius of this cavity. So it is due to the single spark. Now the energy converted into the single spark is given by ES, that is the VIT on. That means for how much time the pulse is on. So depending upon that VI into T on, we can conclude this is the energy content of a single spark. Now energy available. What will be the energy available? EW is directly proportional to ES with the constant K. So EW equals to K into ES. Now from that we can say that it can be logically assumed that the material removal in a single spark would be like tau S is directly proportional to ES is directly proportional to EW. Okay, where tau S equals to G into ES. So now we can say that the material removal rate is total material removal tau S depending on the total time. It is not the T on. So this is the material removal in the single spark. Now we have to count, or we have to calculate the time. How we can calculate the time? So total time is actually, you can say Tc equals to T on plus T off. So T on plus T off. Why T on and T off, and what is the function of T on and T off? T on, say for 100 minute of time section, only the 20 second will be actually the spark will happen. So this is your T on. Rest of the time, that is say for 80% of the time, is your T off. Why we need T off? Because after a single spark, the burn material will create a sustainable layer on the surface. So when this burn material create a surface or create a layer over this work surface, what will happen? This spark will not happen. This spark will not happen. So after some time, the spark will discontinue and the material removal process will be completely stopped. That's why we need T off time. In this T off time, what we do, we remove this material from this work surface so that a fresh layer can come in front of the tool. So that's why in every machining operation, we have to give some T on time as well as we have to give some T off time. Okay. Now, in a single spark, we have already calculated the total material removal rate is tau s, and we know that this material removal rate is single T on time. So, when we are calculating the MRR material removal rate, we have to include this T off time. So, how we will calculate the MRR? It will be T tau s by TC, that is total time. So, we can convert this tau is divided by T on plus T off by using this equation. So from here we can convert it into MRR equals to G into VIT on. So this is your VIT on divided by T on plus T off. Very simple thing. And then we have changed this T on. We have take this T on over here and similarly over here. So we have just transform this equation, and then we got the final equation that G equals to VI 1 plus T on by T off. So this is your final equation for the MRR. MRR will be G VI by 1 plus T off by T on, and this material removal rate is the volumetric material removal rate during EDM process. Now we have come to the end of this lecture session. So what is the advantage of the EDM process? As we know, as we have seen that there is no direct contact between the tool and the workpiece, so we can use any material, any hard material which is very hard to machining using the conventional machining process. So we can use any hard metal, like any hard alloy metal. Basically the tungsten alloy metal, they are very hard metal. We can use very good quality of final product, so that can be used in the aerospace engineering or medical science or very advanced technology. So these are the very advantages of the EDM process. Like it processes a good surface finish, so the accuracy and repeatability is high, so we don't have to go for the final secondary operation or the finishing operation. So after the EDM process, we can use that material directly into the where we need. The hardness of the workpiece is not a matter, as we know that there is no direct contact. EDM is a bar-free process, so we don't have to go any other complicated process. And the main advantage, due to the presence of the dielectric fluid, there is very little heating of the bulk material. So there is a thermal stress. There are obviously some thermal stress, but the thermal stress is very low. There is some limitation also. The limitation is the material rate is very low. So this is not very economical for bulk order. This is not economical. Okay, this is only economical for the hard and difficult to machine and for very specific region. Okay. There is another disadvantage is there is recast layer and the micro crack due to the thermal difference during the process. So it can create a internal stress also. So there may be some thermal crack due to this process. EDM process is not suitable for non-conductor because in this case the electron flow will not occur. Like if we use a ceramic material, we cannot do the EDM process. Rapid electrode wear makes the process very costly. In case of ECM, the electrode wear were not very prominent, but in case of EDM process, the electrode wear is very prominent. So this is the main disadvantage of the EDM process. The surface produced by the EDM generally have a matte type of appearance. Maybe sometime it require finishing operation, but it is not always required a secondary operation. But sometimes we go for the polishing operation also. So these are the disadvantage of the EDM process. So thank you everyone. Thank you for listening this lecture.